Now the STM32F411 also has external interrupt or event controller, and it consists up to 23 edge detectors for generating event or interrupt requests. So these are not exactly peripheral interrupts, as we shall see shortly. These are generally interrupts that are coming from lines outside of the controller, generally. Though we can also generate an external interrupt from software, which is called an event request, but generally these will be interrupts that are coming into the ports of the controller. Now, each input line can be independently configured to select the type, that is, whether it's an interrupt or an event. Interrupt would mean it's a physical signal that is sent into the processor to interrupt it, and how the trigger happens. For example, the trigger could be a rising edge trigger or a falling edge trigger. So we don't have a level trigger in the case of interrupts in the STM32F411. Each line can also be masked independently. Now, a pending register maintains the status line of the interrupt requests. Now, this pending register is separate from the NVIC pending register. We shall see when we are looking into the code that when an interrupt is asserted, an external interrupt is asserted, we have to clear the pending status going into the external interrupt controller registers also to disable that interrupt for that particular time, because otherwise the interrupt remains asserted. So this is something that we have to keep in mind, and we'll see that shortly. Now this is a map of how the external interrupts are related to the ports of the controller. So in the case of STM32F411XC or XE, we have ports A to E, and port H is used for 2 pins of port H is used. So that's for a different purpose, but in general, it is port A to E. Now, as you can see in this slide here, these are all the pins for port A. That is, there are 16 pins for port A, 16 pins for port B. It goes on for port C, port D, and then up to port E. And this might look illogical, but these arrows should have been dotted actually. Okay, I have put these arrows as solid arrows, but if had it been dotted, it would have conveyed the meaning better. This means that these are the same external interrupts. So EXTI0 to EXTI15, as they are called, that is the interrupts that are connected to the outside ports. I'm not talking about the remaining EXTI interrupts. We'll talk about them later. So this is not exactly a connection diagram. This is a possibility diagram, you can say. So EXTI0 can be connected to port A0, port B0, port C0, D0, or E0. Similarly, EXTI1 can be connected to either port A1 or B1, so on and so forth. Okay. This one cannot be connected to multiple ports. That is the first rule. Secondly, EXTI0 cannot be connected to other ports. It is only for every port, that is port A, port B, the EXTI0 interrupt maps with the 0th pin of that particular port. So there could be various ways by which we can configure this. For example, we can configure EXTI0, 1, 2, 3 to have send signals into port 0 to port say 3. So these EXTI lines are used up. So from 4, 5, 6, 7 we can have 4, 4 and 5 in port B4, and then 10, 11 in port E, and so on and so forth. So there could be various combinations of setting up the EXTI interrupt as per our need. How is this accomplished? So The next diagram is a standard diagram that you will be seeing in many data sheets, but I thought that this slide is necessary for you to get a better idea. So coming to the next slide, this is how it is represented generally. So what we saw in the previous diagram, that is port A0, port B0, port 2, port E0, are all shown to pass through a multiplexer. And this is the EXTI0 line that comes out. So this multiplexer is again configured through the syscfg ext cr1 register. So this is one register that configures this particular multiplexer. So it says that whatever is the, say if it's a value 0, then it will mean port A0, and then you have EXTI. So in this particular register, fields from 0 to 3, that is 4 bits, decide which port it is going to service the external interrupt. Similarly, here the bits are 0 to 3 and it goes on till EXTI15 this way. Okay, so this is syscfg EXTI4, so 0 to 3 would mean this is a separate register. So again, it is these are the first 4 fields for that particular register. This is how the pins are selected for external interrupts. Now there are other 5 external interrupt lines. For example, the EXTI line 16 is connected to the PVD output, EXTI line 17 is connected to RTC alarm, EXTI line 18 is connected to USB OTG FS wake up event, 21 is connected to RTC tamper and timestamp events, 22 is connected to RTC wake up events. So these events, they are again connected to fixed lines or fixed events. Okay, we will in our case we will be more concerned about configuring the pins and setting up the EXTI interrupts. In our case, it will be the EXTI 0 interrupt connected to port A0 on our board, on the discovery board. So we will be configuring that in the code. Now here is the block diagram for the external interrupt event controller. Now we have the APB bus here, and this is the peripheral interface with clocks going into this block. Now all the configuration that we need to do for these registers will be done over this bus. That is, whatever code we write to configure these 5 registers and this 6 registers will all be coming through. And this is the mechanism for everything. Whenever we intend to configure any register for any peripheral or anything, this is how it is done. So it all comes over on the either the APB or the AHP bus. Now we can see some registers here. That is the pending request register, interrupt mask register, software interrupt event register, rising trigger selection register, falling trigger selection register, and we have another register here called event mask register. Now the external interrupts can be triggered through hardware as well as software. Now we have also seen that other interrupts, peripheral interrupts, can also be triggered through hardware and software by setting the pending bit of the respective interrupt. It is similar here. Now let us have a closer look at the block diagram. So we have 2 AND gates here, and this is an OR gate. We have the interrupt mask register here, which is for the EXTI interrupt requests. Okay, and we have an event mask register here. Now for every interrupt we have to set whether the interrupt should be triggered on the rising edge or it should be triggered on the falling edge. In fact, an interrupt can be triggered both on the rising and the falling edge if we so wish to configure it. Now let's assume that an external interrupt has come in through this input line from some pin. In our case, for our board, it is port A0, and it goes through the edge detect circuit. Edge detect circuit, these 2 registers will govern the edge detect circuit. So suppose we have configured it for a rising edge trigger. So whenever a rising edge from that particular pin is detected, so see there are 23 lines coming in here. So say PA0, say it's line number 1 comes into this OR gate. Okay. Now when it comes into this OR gate, it passes through here and comes to the input of this AND gate. Now if that particular interrupt is enabled here, say the first interrupt, if in my case, say it is EXTI 0. So if that is enabled here, then the AND gate, the output of the AND gate is 1 and it enables the pending request register. The moment the pending request is raised, the interrupt goes into the NVIC and the interrupt gets serviced. If this interrupt mask register was not enabled for that particular interrupt, it would come up to this AND gate, but it will not pass through here. So this is one scenario. If the same interrupt was configured for a falling edge, this whole thing will happen for a falling edge. If it is configured for both the rising and falling edge, there will be 2 triggers, one on the rising and one on the falling edge for that particular pin. Now, assuming that now we want to raise a software interrupt. Okay. So again, software interrupts can be raised for interrupts and events. So we saw in the previous slide here that there are some EXTI interrupts where some EXTI lines are actually connected to certain peripherals. Okay. So now what can be done is, for those peripherals again, if we set the event mask register for those peripherals, and suppose an event comes from here and we have that particular event mask register set here, then it comes out through here and it generates a pulse. And this pulse that is generated through this AND gate does not go to the NVIC interrupt controller. Rather, it goes into the core, that is Cortex M4 core or any other Cortex processor core that you have. So this event has got nothing to do with an interrupt now. Now, what is the use of such a pulse? As we will see here in the data sheet, such a pulse can be used for wake up event management for the processor. So if an event is generated, say it's an external event, for example, it comes from an external pin, or an internal event from a peripheral, or an event raised through software, it can be made to pass through the pulse generator and fed into the core of the Cortex M4. Now there are multiple ways of wake up. So this is the first way. We will not talk about this much. This is the conventional way of handling an interrupt. So whenever an interrupt is raised during an NVIC interrupt is raised during sleep, the processor wakes up and certain steps need to be taken. We are more interested about this. That is the second point. That is when, say, you configure an external or internal EXTI line in event mode, something interesting happens. That is, whenever you put the processor in sleep with the WFE, that is a wait for event instruction, whenever there is an event, for example, we saw that we create a software event or a hardware event or any other event, the processor wakes up. So a pulse is generated, it goes straight to the core and the processor wakes up. But pending bit of the NVIC is not set here. Okay, so we do not need to do anything with so this event has got nothing to do with the NVIC or the IRQ channel, because this does not set the pending bit at all. So this is the use of the event pulse that goes out through here. So there is a distinction. This line, that is, if you treat the EXTI lines as interrupts, it goes to the NVIC. If you treat the EXTI lines as events, then it goes out through here. And as we saw, one of the major roles of such an event is to wake up the Cortex M4 processor from a sleep state. That is one scenario. That is the second scenario where interrupts come out through here. That is the line 16 PVD output, USB OTGFS wake up, and so on. The third scenario is we raise an interrupt through software. That is, through our code we raise an interrupt. Okay. In that case, if we raise an event here in that software interrupt event register, it goes through this OR gate. Here again it checks for the mask and then it goes out. So this is the block diagram for external interrupt event controller. Now let us have a look at the registers and try to understand better how this works. So we will go to the reference manual this time. So we are not going to the programmer's manual, neither are we going to the data sheet. Now we will have to go to the reference manual to have a look at these registers. So this is, you have to be alert about these things, because not all data, as we discussed, not all data will be is confined in one data sheet. It's spread across multiple data sheets. So in this case, if you have to check for these registers, we have to go to the reference manual. So let's go to the reference manual and see what the registers contain. All these 6 registers. So the first register that we come to, that we saw in the diagram also, is the interrupt mask register. So this is a very important register. If we do not unmask the interrupt line in this register, the interrupt will not work straight away. So that is these are the EXTI interrupts that I'm talking about now. So again, each of these bits can be set to 1 or a 0. So if it is set to 0, it is masked. If it is set to 1, it is not masked, in the sense it is enabled. Coming to event mask register, so this is for the interrupts. That is, if you send a signal through an external interrupt pin, this is the register that need to be configured. Now comes the event mask register. The event is basically if you are triggering the interrupt from some peripherals, the 6 peripherals that we saw, and if we are triggering the event from software. So that is where these interrupts need to be enabled. So similarly, you have 23 lines for these events also, because each of these EXTIs can be mapped to either an interrupt or an event. So this will also need to have 23 fields or 23 bits. Then comes the rising trigger selection register. That is, for each of these interrupts, what should be your trigger? So if you set a 1 here, it means this particular interrupt is set for the rising trigger. TR6 means EXTI6 is set for the rising trigger, and so on. Okay. Then you have the falling trigger selection register. So it repeats for all the interrupts again. So you can set a 1 for enabling the falling trigger. So if you want to set for both, like we discussed, you can set for the rising trigger and the falling trigger both. Okay. Here, that is falling edge trigger. Now we have the software interrupt event register. Now software interrupt event register is where you set an event or trigger an event, EXTI event through software. Okay. So it says if the interrupts are enabled on the EXTI IMR register 1 to SW IER bit, when it is set to 0, sets the corresponding pending bit in the pending register. The register thus resulting in an interrupt request generation. Okay. And this bit is cleared by the next register that we are coming to. So this is the software interrupt on line X. If we go to the diagram now, that is the block diagram that we were going through, and just have a look at the diagram, it will become more clear. Now, please note here, now the software interrupt event register, this OR gate, one output of the OR gate goes to the AND gate here and another output goes to the second AND gate. So all the software interrupt events that are triggered in the SWI-ER register, the register that we are currently seeing in the reference manual, goes to both the AND gates. Now, if the interrupt mask register for that particular interrupt is disabled and the event mask register for that particular event is enabled, the same one, the same line, then the pulse will come out through here. Otherwise, if the interrupt for that particular line is enabled, then the pulse will come out through here. So that is the logic. So following that logic, in the data sheet or in the particular reference manual, this register should activate interrupts in either cases. That is, if the corresponding interrupt mask register is enabled or the event mask register is enabled. So the same interrupt, besides the 6 that we saw previously, same interrupt can also be treated as an event. For example, EXTI0, instead of configuring it to talk to port 0, we can also do a software trigger of that particular interrupt, and then that has to pass through the, if we consider it as an event, then if it could pass through the event mask register. So once you are comfortable with coding on this particular board, it is imperative that you start experimenting with these. So we will see one scenario here, that is PA0 interrupt enabling, but then there are multiple scenarios that you can try out here, whether and a particular interrupt line can be considered as an event or an interrupt, and follow this diagram right all along. This diagram has got a lot of information in it. So when you are configuring the registers also, if you refer to this diagram, you will not go wrong in configuring your interrupts. And we will follow this diagram when we are configuring our PA0 interrupt also. Now coming to the pending register. Now whenever an external IRQ is triggered using either software or hardware, then the pending register is enabled. But the pending register is not enabled for events. So if we look at the diagram, again, the block diagram for the controller, we will understand what we are discussing here. So if an event is generated, it goes through this path. So it does not set the pending request register. If an interrupt is raised, for example, if we are raising an interrupt through software, then it goes through this path and sets the pending request register. So software events, when raised, takes this path, the bottom path, and checks with the event mask register and goes out through here. That there it does not set the pending request register. So you have to remember that. So this is the pending register for that particular purpose. Now, this pending register is not the same as the pending register that we have in the NVIC. This pending register needs to be for IRQs, external interrupts, and an external interrupts even triggered through software. This pending register needs to be cleared. Otherwise, this interrupt will be in a constantly asserted state. And we shall see that when we are looking into the code. So here are the steps to set up external interrupts. Now we will be seeing a code example shortly. So the first step is to decide which external interrupt to use. On our board, we have the EXTI0 connected to port A0 through an active high button, that is the user button. So we will be setting up EXTI0 to fire for port A0. Now, as we saw in the multiplexers in the previous slides, we will need to choose the port for which we will be using pin 0. And that register is syscfg EXTI CR1. This is one register that we haven't had a look at because it didn't fall in either the NVIC or system control block. But let us have a look at that register now. Rather, it is a group of 4 registers which maps the interrupt lines to the pins. Now for this, we are again referring to the reference manual, and this is in chapter 7, page 141. So as we discussed, there are 4 registers in this group, that is syscfg 1 through 4, and what it does is, so each field is 4 bits. We discussed about this in one of the previous slides. So each field has 4 bits. So this represents EXTI 0, this represents EXTI 1, 2, 3, and it goes on till EXTI 15 for all these 4 registers. So if we see what these registers do, so 4 bits stand for 0 to 15. So as we know, EXTI 0 is meant for port A0, port B0, port C0, D0 and E0. Now these two are reserved here because, as we discussed, STM32F411XE and XC does not have, it only has till port E and port H. So the other bits are going to be reserved. So we can set, so in our case we have to set 0000 for it to map to port A0 pin. Okay, so since this is for EXTI 0, we have to set it to 0000 to map it to port A0. If the user button was connected to port D0, then this field would have had to be 0011, and we'll see that in the code. Similarly, for the second register, again it goes from port A through to port H, but this is for EXTI 4, 5, 6, 7, EXTI 8, 9, 10, 11, and EXTI 12, 13, 14, 15. So this is how it is. So for a clearer picture, again, if I go back to that diagram of the multiplexers, you might have a better idea of what we are discussing here. So we saw these multiplexers previously. Now what these registers are basically doing is, depending on a value that you are setting here, for example setting 0000 in that EXTI 0 register, PA0 is mapped to EXTI 0, and so on and so forth. So that is what is actually happening, and each of these multiplexers represent one 4-bit field in the registers. So each of these multiplexers will represent one 4-bit. So this goes to one multiplexer, this goes to another multiplexer, so on and so forth. So this is how this is arranged. Now once that is set up, we have to configure port A as an input port. So this is purely IO configuration, and we have discussed about IO configuration in another section. But since the interrupt goes in through a port, of course the port has to be enabled. The clocking to that particular port has to be enabled, and port A0 actually has some restrictions. These restrictions are not going to hinder our programming, but since in our board the user button is connected to port A, we don't have a choice. Then we'll have to enable interrupt line 0 in the EXTI IMR register. So we saw the EXTI IMR register. So interrupt line 0 is going to be the first bit, which we set to 1. Then we will set a rising edge trigger in the RTSR register, which we also saw in the programming manual. And for external interrupt, there's a separate external pending register. So we have been repeating this. So this is just a diagram of what a rising edge and falling edge is of a particular signal. So when the signal is going from 0 to 1, it's called a rising edge. This is the level edge, and this is the falling edge. After that, we need to configure the nested vector interrupt controller ISC are 0 for ext. That is, we have to enable ext and there. Besides unmasking it here in the exti IMR, two places. And of course, we need to check the interrupt number from the particular vector table for the SOC being used. So here in the NVIC ISR 0 for EXTI 0, it is actually interrupt number 6. So we have to go to this particular register and set interrupt number 6. So there is actually a confusion happens here, because setting line 0 here is bit 0, but here it is not bit 0. It is bit 6 in the ISR. Then we have to set the EXTI 0 interrupt priority in the NVIC priority register. Okay, and we are again repeating it, saying that there are two places to unmask the interrupt. One is in the peripheral. In this case, it is the EXTI circuit, and other one is the NVIC. Now, for software trigger of interrupts, we have been discussing about software trigger of interrupts. This is just to summarize what we have discussed so far. So exceptions in interrupts can both be triggered with software code. This method is needed. So why do we need this? So this method is needed by unprivileged tasks to access some system services only, accessible in the privileged mode. So suppose we have some unprivileged tasks which need access to certain services, and it cannot access those services while being in the unprivileged mode. Say it is an RTOS task. So what it does is it raises a software interrupt, and once it raises an interrupt, it goes into the handler mode. Going into the handler mode gives it the privilege to access the system services. Of course, there could be a few clock cycles delay in starting of the interrupt. We saw that we discussed about that when we spoke of interrupt latency. Even if the priority is higher than the current level. So there could be some delays. To have the interrupt handler execute before the next operation, memory barrier instructions need to be inserted. So memory barrier instruction. So basically, the Cortex M4 is a pipelined architecture. So it has a fetch, decode, execute pipeline. So basically, when an interrupt is asserted, there is a tendency, if there are instructions coming in the pipeline after the instruction where the interrupt occurred, there is a possibility that an instruction or two after the current instruction at which the interrupt has occurred gets executed. To prevent that from happening, say we don't want any other instruction to be executed once the interrupt comes in, we will clear the pipeline. So when we clear the pipeline, there are no instructions in the pipeline. So we'll clear the pipeline through software. So there are no instructions coming in, the relevant instructions coming in the pipeline. So the pipeline will probably be filled with no operation, NOP or something. So the interrupt gets triggered and the ISR is entered even before other instructions are executed on the core. Now, the pending status of the interrupts above 16 can be set by writing to interrupt set pending register or software triggered interrupt register. Okay. So above 16 would mean 16 and above 16. Okay. So 16 and 16 plus. For other system exceptions like NMI, PendSV, SysTick, we trigger them by setting the pending status in the interrupt control and state register. Like in interrupts, setting the pending status of these exceptions does not always guarantee that they will be executed immediately. So even for system exceptions, it does not guarantee that it is going to be executed immediately. There could be some delays. So this is an exercise for you. Try out the PendSV system exception as an exercise. So the exercise is write code and set a breakpoint in the PendSV handler in such a way that when you trigger the PendSV interrupt, it goes and gets the control goes and hits the breakpoint in PendSV. Set some priority for the PendSV and you could try some preemption exercises also on this particular interrupt.